A good model doesn't just hand you a decision. It lets you ask a simple, powerful question. Why? That ability to see the reasons behind a prediction is called interpretability. It's what turns a mysterious model into one you can actually trust, debug, and defend. Here's the fear. An application goes in, and one word comes out, denied. But the box gives no reason. And if nobody can see why, then nobody can trust it, nobody can challenge it, and nobody can fix it when it's wrong. The good news is that for most models we can open that box. We'll ask two different kinds of question. The first is global, across everyone. Which features matter most? The second is local. For this one person, why did the model decide the way it did? Before either, let's build the one idea everything rests on, what a weight actually does. Take this applicant's income. It sits about 1.5 standard deviations above average. The model multiplies that by the weight it learned for income, about 1.2, and the result is a push of roughly plus 1.9 toward approval. Every feature does exactly this. Its value, times its weight, is its push. Now the global question is easy to answer. A bigger weight turns any given feature value into a bigger push. So the size of the weight is the feature's importance. Let's line the features up by it. Here they are, straight from what the model learned. Debt ratio has the largest weight, so it matters most. Then income, then late payments, then the length of credit history. There's a subtlety we have to handle, or the comparison is meaningless. Features live on wildly different scales. Income runs into the hundreds of thousands, while debt ratio sits between 0 and 1. A raw weight on income would look tiny just because income's numbers are so large. So before comparing, we standardize. We rescale every feature to how many standard deviations it sits from its mean. Only then are the weights on equal footing, and that's exactly the comparison the bars showed. Each weight also carries a sign, a direction. A higher income pushes toward approval, and so does a longer credit history. A high debt ratio and more late payments push the other way, toward denial. Global importance is useful, but it describes the average applicant, not any real one. For a specific person we go local. We break their score into the individual push from each of their own features. Here is our applicant. An income of $88,000, a debt ratio of 0.55, 12 years of credit history, and 3 late payments. Some of that looks strong, some looks risky. We start the running score at the base rate, 54%, what we'd guess before looking at anything specific about them. Now we let each feature push that number, left toward deny or right toward approve, one at a time. First, their strong income. It pushes the score up, toward approval. So far, so good for this applicant. Then their debt ratio, which is high. It pushes back the other way, and further than income lifted it. The probability swings down, below the halfway line. 12 years of credit history nudges the score back up a little. Then 3 late payments drag it down again. Every feature has now had its say. The pushes settle at 36%, below the halfway line. The decision is deny. And now we can explain it in one honest sentence. Strong income and history spoke for this applicant, but a high debt ratio and late payments outweighed them. Here's where interpretability becomes really powerful. Let's ask a what if. Suppose this same applicant had a lower debt ratio, say 0.20 instead of 0.55. We change only that one number and rerun the pushes. Watch, the debt push now flips to helping, and the probability climbs all the way to 97%, an approval. One feature was the difference between no and yes. This is why interpretability matters in the real world. Trust, people accept a decision they understand. Debugging, you might catch the model leaning on a feature it should never use. Fairness, you can check what it's really basing decisions on. And sometimes the law simply requires an explanation. One honest trap to know about. Importance can be misleading when features are correlated. Debt ratio's importance on its own is 1.53. But watch what happens if we duplicate it, add a second, identical copy. The model splits the credit between them, 0.77 and 0.77, which still add back to 1.53. A genuinely important feature can look weak simply because it has a twin. So read importances carefully, and never mistake them for proof of cause. So, to recap, a push is just a feature's value times its weight. Global importance tells you which features matter overall, once they're standardized. A local explanation tells you why one specific decision came out the way it did, push by push. A counterfactual shows you what would flip it. And remember the trap, correlated features share credit, and importance is never proof of causation. Next, we use these very tools to ask a sharper question. Is the model fair across different groups of people?